In the last lecture, we had initiated discussion of correlations for heat and mass transfer. I had said that there are two important considerations here. One is the flow regime, whether it is laminar or turbulent flow, and the other is the surface conditions, whether you have a no slip condition or a slip condition at the interface. In this case, the dependent parameters are the dimensionless fluxes, the Nusselt number and the Sherwood number, and the independent dimensionless groups are the ratio of mass or heat convection and diffusion, that is the Peclet number, and the momentum convection and diffusion, that is the Reynolds number. The Peclet number determines the relative magnitudes of mass or heat convection and diffusion. The Reynolds number determines the relative ratio of the momentum convection and diffusion, which determines the flow pattern. Okay. So, those are the independent and dependent dimensionless groups. I discussed some general considerations. One is laminar and turbulent flows. These have very different characteristics, as we had seen earlier in our discussion of pipe flows and flows around a particle. The correlations will be different in these two cases, and the surface conditions. Now, when the Peclet number is small compared to 1, okay, there are two regimes. Of course, you can consider limits. One is where the Peclet number is small, and the other is where the Peclet number is large. Peclet number is small, velocity is no longer a parameter. Therefore, the Peclet number and the Reynolds number are no longer parameters. Transport is due to diffusion, and the Sherwood and Nusselt numbers have to be constants. That is a dimensional necessity. And as I said, for the flow around a particle, the Sherwood and Nusselt number have to be 2. This low Peclet number regime is not of relevance for flow in conduits, because in this regime the temperature or concentration equalizes across the cross section before the fluid has moved a distance even small compared to its diameter, and therefore, there is no advantage to having a long pipe. Then we looked at high Peclet number laminar flow for a pipe, or high Peclet number low Reynolds number for flow around a particle. In this case, the velocity profiles are linear functions of the driving force. So, if you change the average velocity by some factor of 2, or you change the pressure gradient by a factor of 2, the velocity at each point in the fluid changes by that same factor. So, the profile remains the same, the pattern remains the same, only the magnitude of the velocity changes, the characteristic velocity. Similarly, for the flow around a particle, if the free stream velocity changes by a factor of 2, the velocity at each point will change by that same factor. So, all of the information regarding convection is contained in this characteristic velocity itself, the free stream velocity for flow around a particle or the average velocity for flow in conduits. Therefore, the Nusselt number or the Sherwood number has to depend only on the Peclet number itself. The flow profile does not change, so the Reynolds number does not matter. For laminar flows, low Reynolds number around a particle or less than 2100 Reynolds number for a pipe. And I told you that the scaling laws that we typically get in these cases are P power 1/3 for the flow past a rigid surface with a no slip condition, and P power half for the flow past a mobile interface where the velocity is non-zero and the shear stress is 0. And of course, if we go to high Reynolds number and high Peclet number, then there is the Nusselt number and Sherwood number are functions of both the Reynolds number and the Peclet number. We had looked at correlations for pipe flow. Laminar flow, the Nusselt number or the Sherwood number depends only on the Peclet number, power 1/3, because there is a no slip condition at the surface, times a factor that is the ratio of the diameter and the length, that to the 1/3 power. Okay. High Reynolds number, okay, the Nusselt number or the Sherwood number depends on Re power 0.8 times PR or SC, okay, or SC power 1/3. Okay. Prandtl number for, I am sorry, this is for the Nusselt number. You would get the correlation for mass transfer by substituting the Sherwood number for the Nusselt number and the Schmidt number for the Prandtl number. Okay. And it can be written in terms of the Peclet number alone. So, from this you will get the expression for the Colburn J factor. Okay. It is only a function of the Reynolds number in this case, plus the ratio of viscosities. Okay. And yeah, sorry, I have to have a factor of d by L power 1/3 here as well. Okay. This factor of d by L power 1/3 is present both for the low Reynolds number correlations and for the high Reynolds number turbulent flow correlations. Okay. So, kindly make that correction. Okay. That factor of d by L power 1/3 is present in both cases. Okay. Okay. So, and I had shown you a practical example where this can be used. Okay. I had shown you a practical example where this can be used. Let us go next to the flow past a flat Peclet. Okay. And I told you when we did momentum transfer that there is a boundary layer whose thickness, okay, delta 0.99 increases proportional to x power half for the laminar region. Okay. Okay. And then it undergoes a transition where you have a turbulent flow. Okay. And there it increases x power 1/5. Okay. Okay. In this case, the heat and mass transfer correlations depend upon whether the flow is laminar or whether the flow is turbulent. In this case, the Reynolds number is defined as rho V free stream L by mu based upon the total length of the plate. Okay. And the Peclet number is equal to V free stream, okay, L by alpha or L by D. This case, the Nusselt number and the Sherwood number, okay, for a laminar flow, the correlation is Nusselt number is equal to zero 0.664, okay, RE per half and PR per 1/3. And usually have a factor of mu by mu w per 0.14. Okay. In this case, there is no ratio of diameter and length. Okay. In this case, we do not have the d by L ratio because there is only one length scale, the length. Okay. In the case of a pipe, we had a diameter and a length. Okay. And for a turbulent flow, the correlation is of the form the Nusselt number is equal to 0.037 RE per 0.8, okay, PR per 1/3 mu by mu w. Okay. You can see that the forms of these empirical correlations, the dependences here are very similar, okay, except that you have a RE power half in the case of a laminar correlation. Okay. So, other than that, the nature, the forms of the correlations are very similar. Okay. This is for a turbulent flow. Okay. So, you have correlations for both laminar and for turbulent flows. Okay. Laminar flow for RE less than 5 into 10 power 5, okay, based upon the length. In turbulent flow, the Reynolds number is greater than 5 into 10 power 5. Okay. Then finally, we come to flow around a particle. we had already discussed, okay, spherical particle, okay, low Peclet number, the Nusselt number is a constant for a spherical particle. That constant is equal to 2, okay, that we had already discussed for the low Peclet number limit. High Peclet low Reynolds number, okay. In this case you can actually derive this. I told you that the transport coefficients go as Peclet number to the 1/3 power when you have a no slip condition at the surface. So, we are considering a particle at whose surface the velocity comes to 0 at that surface, okay. A particle whose velocity comes to 0 at that surface, and you know that this has to be proportional to p power 1/3. There is a no slip condition and the coefficient can be calculated, okay. The coefficient can be calculated. This is for a specific case where you have high Peclet and low Reynolds number. As I said, this regime can be realized only when in the case of liquids where momentum diffusion is much larger than mass diffusion, okay. It cannot be realized in general case gases because both momentum and mass diffusion are the same. Normally correlations are used over a broader regime encompassing both laminar and turbulent flows, okay. I will give you two examples of these correlations. These are not exhaustive, okay. For specific applications there will be specific correlations that are known within the domain, okay. I am only giving you these as representative correlations that can be used for quick estimates, not for detailed estimates which will have specialized correlations, but only for quick estimates. And these correlations work reasonably well with an error margin of about 30% or so, okay, over a range of Reynolds numbers and Prandtl numbers or Reynolds numbers and Peclet numbers, okay. So, these should be used only for estimating, but not for actual design, okay. There you should use more accurate correlations which should be available for specific configurations in literature. The Nusselt number for this case minus the value for low Peclet number. I told you that in the absence of convection the Nusselt number is equal to 2. So, these correlations are usually written for the difference between the Nusselt number and the value that it has in the limit of low Peclet number when there is only diffusion, okay. This is equal to 0.6 Re per half PR per 1/3, okay. This goes by the name of Rand's Marshall correlation. Okay. And there is a more detailed correlation which is Nu minus 2 is equal to 0.4 Re per half plus 0.06 Re per 2/3, okay, times Prandtl number per 1/3, okay. So, these are the types of correlations that you will find in literature, okay. So, I will not go into details of all the different types of correlations that are there. Some are relevant in some situations whereas others in other situations, and you should choose the correlation from literature depending upon the specific problem that you are considering. I will just focus on how these can be used to derive actual estimates, okay, for design of processes. So, I will give you an example, okay. In the beginning of this course we had discussed a spray dryer, okay. In the beginning of the course we had discussed a spray dryer, and there it was desired that there were droplets that were sprayed into a gas that was moving upwards, dry hot gas, and it was desired that all of the moisture in the droplets has to evaporate before the droplet hits the side of the spray dryer, okay. That was the design consideration, and as I had explained at that time, this involves a combination of mass and heat transfer. Okay. Both mass and heat transfer are involved in this. So, in this problem I will just try to estimate what is the time taken for mass transfer, okay, to evaporate all the droplets, okay, from the water, all of the water from the droplets into the dry air. Okay. And combined with that, I will also try to find out what is the temperature difference I have to maintain between the droplets and the air in such a way that all of the heat required for evaporation is transported into the droplet by the time the droplet, so that the droplet evaporates within the time it takes for mass transfer. Okay. So, those are the two things that I will consider in this case. Okay. So, specifically droplets of diameter 1 millimeter, sorry 0.1 millimeter, okay, and density 10 power 3 kg per meter cubed, containing 80%, 80 mass percent of water, okay, are dried to porous particles of the same diameter. Okay. At temperature 20 degrees centigrade. Okay. The temperature of the droplets which is ejected is at 20 degrees centigrade. Okay. At velocity 1 meters per second. Okay. That is the velocity, free stream velocity. What is time for drying? Okay. What should be air temperature? Okay. That is the what should be the temperature of the air. Obviously, the temperature of the air has to be higher, so that heat is transferred from the air to the droplet. Okay. Okay. Vapor pressure of water is 2.3 kPa at 20 degrees centigrade. Okay. And the properties, okay, of air: rho density is equal to 1.095 kg per meter cubed. Okay. The viscosity is equal to 97 into 10 power minus 5. Thermal conductivity, okay, K equals 2.8 into 10 power minus 2 watts per meter per degree centigrade. Cp is 10 power 3 joules per kg per degree centigrade, and the diffusivity of water vapor in air. Okay. So, these are the conditions given. Okay. So, now we have to estimate what are the dimensionless groups in this case. Okay. The independent dimensionless groups, Reynolds number for fluid flow, Prandtl number for heat transfer, and the Schmidt number for mass transfer. Okay. So, let us do that. Okay. The Reynolds number is equal to rho V free stream d by mu. In this case, it is going, the droplet is passing through air. So, you have to consider the air properties. Okay. Is equal to 1.095 kg per meter cubed into 1 meter per second was the ejection velocity into the droplet diameter. Droplet diameter was 0.1 millimeters. Okay. So, this is 10 power minus 4 meters divided by the viscosity, which is 1.97 into 10 power minus 5 kg per meter per second. Verify quickly that this is dimensionless and the value is 5.6. Okay. Prandtl number is equal to Cp mu by k, which is 10 power 3 kg per joules per kg. Okay. Okay. Into mu, which is 1.97 to 10 power minus 5 kg per meter per second, divided by k, which is 2.8 into 10 power minus 2 watts per meter per degree centigrade. Dimensionless, once again, it is equal to 0.70 approximately. And the Schmidt number, which is mu by rho d. Verify once again it is dimensionless. This turns out to be equal to 0.6. Okay. So, now we have the Reynolds, Prandtl and Schmidt numbers, and from that we have to determine the dimensionless fluxes, and from that back out what are the dimensional fluxes. Okay. So, the dimensionless fluxes are the Nusselt number and the Sherwood number. I will use here this, okay, what is called the Whittaker correlation. Okay, to calculate the dimensionless fluxes. Okay. The Nusselt number is equal to 2 plus 0.4 into 5.6 per half plus 0.06 into 5.6 per 2/3, Reynolds number per half and Reynolds number per 2/3 times the Prandtl number per 1/3, okay, which is 3.01. And the Schmidt number, the Sherwood number 2 plus into 0.6 per 1/3, about 2.96. Okay. So, these are both of order 1. Okay. These are both of order 1. Okay. Now, from this we have to find out what is the time required for the water to evaporate. Okay. From one droplet, okay, mass of water in droplet okay, Note that water formed about 80% of the droplet. Okay. Water was about 80% of the droplet, and the droplet density was 10 power 3, diameter was this. So, mass of water in droplet is going to be equal to 80% of the total mass, okay. That is 0.8 into the total mass. Okay. Mass is equal to the density 10 power 3 kg per meter cubed. Okay. So, let me just write this as the density rho into the volume pi d cubed by 6. Okay. The volume of the droplet in terms of the diameter is pi d cubed by 6. Okay. It is equal to 0.8 into 10 power 3 kg per meter cubed into pi into 10 power minus 4 by 6. And you can work out this calculation. It comes to about 4.2 into 10 power minus 10 kg. That is the quantity of that is the mass of water that has to be evaporated. Okay. What is the mass transport rate? Okay. Mass transport rate is equal to the average flux, okay, average flux into the surface area, okay, pi d square. Okay. The average flux into the surface area, okay, and the average flux can be written as the Sherwood number into d delta c by the droplet diameter into pi d square. Okay. So, I have to find out what is the concentration difference between the surface and the bulk. In the bulk, of course, I have dry air, and therefore, the concentration of moisture in the air is 0. What about at the surface? Okay. I have to evaluate what is the concentration based upon the partial pressure 2.3 kilopascals. Okay. Okay. You can estimate that using the ideal gas law. Okay. The concentration at the surface is equal to the vapor pressure, okay, P by K T, okay, is equal to the number of moles per unit volume, the molar density. Okay. I have to multiply that by the molecular mass. Okay. I use molecular mass if I use the Boltzmann constant, the molar mass if you use the ideal gas constant. In both cases you will get the same answer. Okay. So, this is equal to 2.3 into 10 power 3 Pascal. Note that everything has to be done in terms of SI units. Okay. You cannot use different units here. Okay. So, one has to be careful in using SI units. Okay. Into the mass of a molecule. Okay. Mass of 1 gram mole, 18 grams, okay, is 18 grams, okay, which is 0.018 kilograms. This mass of 1 mole, and that contains 6.023 into 10 power 23 molecules. Okay. Okay. So, the mass of 1 mole divided by the number of molecules in 1 mole, that mass has to be in kilograms. The mass of 1 mole is 18 grams. I can also take 1 kilomole in which the mass would be 18, denominator would be 6.023 into 10 power 26. So, both would give you the same result. Boltzmann constant 1.38 into 10 power minus 23 joules per Kelvin into the temperature, which is in this case 293 Kelvin, 20 degrees centigrade as was given. Okay. So, this is equal to 1.7 into 10 power minus 2 kg per meter cubed. Substitute that into the expression of the mass transport rate. Okay. Sherwood number was 2.96 into, I can cancel out this diameter here, diffusion coefficient was 3 into 10 power minus 5, okay, meter square per second. into delta C is 1.7 into 10 power minus 2 kg per meter cubed. Okay, into pi into d. I have one factor of diameter 10 power minus 4 meters. Okay. And you can evaluate this, and this turns out to be equal to 4.73 into 10 power minus 10 kg per second. Okay. So, that is the rate. This is the amount that has to be this is the amount that has to be evaporated. This is the rate of evaporation. So, the time required for evaporation T will be equal to the amount that has to be evaporated 4.2 into 10 power minus 10 kg divided by 4.73 10 power minus 10 kg per second. Okay. This turns out to be about 0.89 second. Okay. So, the entire evaporation is actually taking place within 1 second. Okay. So, this is the time for evaporation. Okay. How about the time for heat transfer? Okay. So, the entire latent heat of evaporation has to be transferred within the time that the droplet mass is transferred out. Okay. So, what is the the latent heat of water of vaporization is equal to 2.3 into 10 power 6 joules per kilogram. Okay. Okay. So, this latent heat has to be used to determine how much heat energy is required. Okay. Heat required for evaporation is equal to this latent heat. Okay. Into mass. Okay. And the mass of the droplet we have already calculated over here. Okay. So, this is just equal to 2.3 into 10 power 6 joules per kg into the mass of the droplet, which is 4.2 into 10 power minus 10 okay, kg. Okay. So, this turns out to be equal to 9.63 into 10 power minus 4 joules. Okay. So, we have the heat that is required. We have to find out what is the heat transfer rate. Okay. Heat required divided by heat transfer rate will give you the time required for the heat transfer. Okay. The heat transfer rate is the average heat flux times the surface area pi d square. Okay. Average heat flux is the Nusselt number by K, average heat flux is the Nusselt number into K delta T by D into pi d square. Okay, because the Nusselt number is Q average divided by K delta T by D. Okay. So, this is equal to pi d K delta T times the Nusselt number. 10 power minus 4 meters is the diameter. Okay. The thermal conductivity is 2.8 into 10 power minus 2 watts per meter per degree centigrade. Okay. K delta T we do not know yet. Okay. That is what we have to calculate. Okay. How much temperature the gas has to be at. Okay. into the Nusselt number, which is 3.01. So, this gives me 2.64 delta watts per meter, I am sorry, watts per degree centigrade into delta T. Okay. That is the heat transfer rate, watts per degree centigrade into delta T, joules per second per degree centigrade. What is joules per second? Therefore, the ratio, okay, the time required is equal to the heat required by the transfer rate. Which is 9.63 into 10 power minus 4 by 2.64. Okay. Sorry, there should be a 10 power minus 5 here. Numerator, you have seconds into degree centigrade, because I have a 1 over watts per degree centigrade in the denominator, which gives me a degree centigrade in the numerator, and I have a joules divided by watt. Watt is joules per second. So, I get second into degree centigrade. Okay. And if I divide by temperature, which has the same dimension as degree centigrade, I will get ultimately the time in seconds. So, this thing has to be the same as the time required in this case for the mass transfer. Okay. And this gives me the temperature difference between the two as 40.9 okay, degrees centigrade. So, the air has to be at a temperature about 41 degrees more than the droplet, so that the heat transfer takes place within the time it requires for the mass transfer to be completed. Okay. So, this is an example of how you design a combined heat and mass transfer process, so that the entire heat transfer gets completed. The temperature difference is sufficiently large that there is heat transfer from the gas to the liquid to the droplet within the time that it takes for the mass transfer to take place due to diffusion. Okay. So, this completes our discussion of flow around a particle along with an example. In the next section, I will discuss flow past mobile interfaces that have a slip condition and flows through packed columns. Okay. And after that, we will discuss the flow due to natural convection. So, I will continue this in the next lecture. I will see you then.